Right, okay, hello and welcome to part 5 of our A-level look at waves. Our last lesson we were looking at superposition of waves and stationary waves, and today we're going to be continuing sort of a theme from there where we were talking about constructive and destructive interference, and we're actually going to be focusing on interference for today's topic. So interference is the addition of two or more waves that results in a new wave pattern. So it's the interaction between multiple waves, what that resultant wave then looks like. So, as we were talking about before, we were talking about constructive and destructive interference. So what actually happens here is we have two waves here which are both in the same phase, therefore the peaks are at the same places and the troughs at the same places. So therefore what actually happens is that these result in an addition of the top and an addition of the bottom. So it actually results in a double amplitude of our wave. Now with destructive interference is where the waves are actually 180 degrees phase to each other. So what actually happens is that they cancel each other out because the top figure and the bottom figure are the same, so they cancel each other out because it's a positive and a negative. Don't get this confused with where we were talking about stationary waves. It only works in a stationary wave because something is being sent forward and reflected back. When we're talking about interference here, we're talking about a wave going in a direction. So if these two waves are actually adding to each other, this results in a flat line because the positive and the negative cancel each other out. And again, the negative and the positive cancel each other out. Whereas here we have a positive and a negative and a negative. So that point makes our positive twice as big and it makes our negative twice as big. So we end up with a double amplitude. So our wave is twice as big. But with here, we have our positive and our negative, which are equal numbers. They're just one's positive and one's negative. So say this is +2 and this is -2. Therefore we end up with 0. Again here, at the bottom, -2 and +2. So therefore our resultant is 0, which is why we end up with a flat line. Now this resulting disturbance or this resultant amount of displacement away from our line of 0 displacement, the resultant wave is called the principle of superposition. As I said, do not get this confused with what happens with stationary waves. The only reason why stationary waves stay the same and they still work at 180 degrees phase angle is because it's being reflected back and the waves aren't technically moving anywhere, where these actually have a direction and have a direct interference with each other. So it's a case of addition and subtraction of the wave amplitudes. Okay? So, this is what the basically different types of waves we can look like. So our white light source that we have, we know that white light is made up of multiple different wave frequencies, and this is what happens here. So we have our red light frequency, our green light frequency, our middle range frequency, and our blue or our ultraviolet frequencies, which are the highest. We then have something which is called monochromatic light. Now monochromatic light is made up of only one light frequency, but they're not necessarily running together. They're not directly tightly packed. They can still spread away or disperse out. Now this laser source, like the laser pen I have in my hand, this what actually does is it actually tightly squeezes those lights in. Those light waves in. It tightly squeezes them together, so it's a maximum superposition. So therefore, our laser here has a much more intense light, which is why, you know, when someone has a laser pen like me and they get a little bit bored, you know, you can see it's a lot more intense than if I had a torch. You would actually be able to see this for a lot longer. This laser that I have here, you can see for roughly about 1,000 miles away. That's 1,000 miles. That would be amazing. 1,000 meters away, you can see it for. So it's a much more intense light than you would see from a torch. If I shone a torch, if I stood 1,000 meters away, I might be able to see it, but I wouldn't be able to hold up a piece of paper and it have actually shine on the paper, where with a laser you can, because all of the waves are focused into that one more direction. So, what we're going to do is we're going to have a look at two ideas here. There's a single slit and a double slit, and we're getting into something which is called diffraction, which in the last lesson, which will be the lesson after this, we will actually go into the full examples of diffraction, but for this case I just want to focus on what's actually happening in this section here, because this section is what is giving us our resultant interference. So we were talking about constructive and destructive waves. Okay, and this is exactly how this is depicted here. So what we've got a light source coming here and it's going through a small narrowing. Now when we were talking about diffraction back in Key Stage 4, we were generally talking about water waves, but this is really not that dissimilar because light waves travel in the same way. They're still transverse waves. So as they go through this small gap, say I have my laser pen here, okay, so we know that the waves from lasers are much more tightly packed. So what we've got here is just a normal light source. Now some of our light will travel straight through here. So what we've got is undeflected light waves. So this is our light wave that's going here and our light wave that's going here. So these light waves are actually, what they're doing is as they get closer to each other, they're in the same phase as each other. So they're being constructively interfering with each other. So this basically means is what we end up is this peak in the intensity of the light that we get on our screen that's being shone through. And what this is called a double maximum, okay? And this double maximum is, as we were talking about, it's double the amplitude of the original light source because it's been constructively interfering with each other. So therefore it's doubled its own amplitude. So that is what happens to some of the light. Some of the light travels along with each other, constructively interfere with each other and create our maximum light. And that is what will happen in the centre. This will be the biggest intensity of our light. Now at the same time, you also have some light waves which will reflect off the inside of this barrier, and therefore what they will result in is something which is called path difference. So as some of this light takes a direct movement straight through, you will have some light that's coming from the outside and diffracting in, or from the other side and diffracting in, or even from the inside and diffracting out. That basically means is that wave that's taken, for example, a wave that's travelling from the centre straight to the centre, so it's travelling straight through, and a wave that's travelling from the outside and travelling through. So we now know, do you know what, that was absolutely terrible example. I'm going to start again. Say we've got a wave, okay, that comes from the centre and moves out. We're going to go out to our dark section that's moved out there. But then we've also got another wave that's gone from the outside and it's moved directly there. It hasn't diffracted away, it hasn't diffracted at all. So this has come to now the concept of what we call path difference, okay? And this path difference is what creates the alternative light that we have out here, our dark sections and our bright sections. Because this red section has technically taken a longer distance, remember your Pythagoras and working out the angles and the lengths of your triangle, you will know that this diagonal length here is longer than the straight path. So therefore it's taken a longer distance, it's taken a longer time to get to the same point as the wave that's gone directly there. So therefore the waves are going to be out of phase with each other, and therefore they're going to be destructive interference between them, which is why we result in a negative, a dark light source, because there's been a destructive interference between the two of them and there's no longer light there. So now you're going to say, okay, so we've got bright light in the middle, we've got dark light, how come we've got another light out here? Well, just as there is some light waves that interfere with each other, there's other light waves that don't interfere with each other at all. So there is still some light that will literally just travel from here, it will diffract out straight there, and it's just on its own. It doesn't have interference with other waves. And this is what gives us our outside light sources, and they will be exactly the same light intensity as our original light source. So remember, our middle one is called our double maximum because it's had a positive interference with another wave. And then we've got our dark sources, which is our destructive interference because the two waves are out of phase with each other. And then our normal, just bright light, just normal state light, which will be the same intensity as the original light wave because they're ones that just travel straight there and not interfered in between. And this is exactly what it looks like. Now this is actually the showing of using a laser and using some white light. As you can see here with white light, as you get towards the outside, you can start to see the dispersion of the light waves. So here is our double maximum where we've had positive interference with the two waves, And again, this is with our laser, we've got positive maximum double, and our white light, we've got a positive double as well. And then as we move outside, on the edges of the white light, you can start to see the dispersion of the different colours. And then they get weaker and weaker as they move out because there's less and less waves there. So again, double maximum, this is our laser, this is our white light. So that's the single slit. So what happens with the double slit? Well, obviously with the double slit, there's going to be more and more interaction between the different waves. There's going to be more and more interference because the light is coming from two sources and it is diffracting out from those two light sources and going into each other. Now the thing is, these black lines, as we're going back here, these black lines are what called fringe, are called the fringe sources or the fringe waves, okay? So in between each one is called a fringe wave. And so each fringe, or it's called a fringe of the fringes of light, are the different ones that we have, okay? So this is when we get to Young's the double split experiment. So what we'd expect to see is that. What it gives us is a much cleaner, a bigger look of exactly what's happening on the waves, because instead of it just diffracting through one source, it's diffracting through two. So it gives you a much bigger range of exactly how the wavelengths work. And so that you can just see that by the use of white light. It splits up these lights much easier, much better, so you can see the full spectrum of the white lights that's involved. Again, in the middle is our brightest, it's our maximum double, where the light just isn't being diffracted. But then as you move out, the more interference is happening, more diffraction is happening, so that there's more black lines and there's more sections because we've got two sources interfering with each other. So it gives us our full spectrum there. Okay, so what we're going to do is we're going to work out what this fringe spacing is, how to work out fringe spacing. So the way we're going to do that is we're going to take an example. We're going to take the example of my laser pen. Okay, so the fringe spacing is the distance in between each set of lights or each dark space. Okay, so we've got our equation at the top here, which fringe spacing, which is denoted by W, is equal to our lambda, which is our wavelength, times by the distance, so the distance from the splits to the screen, and that's divided by S, and S is the distance between the two slits, so with the distance from here to here. So obviously that's going to be really, really small. So in order to be able to diffract light easily, obviously as we discussed way back in Key Stage 4, the difference between light and water diffraction is that obviously the water waves are much larger than light waves are. So in order to diffract light waves, the holes must be really, really small. So what we'll do, we're going to give it a go. So our wavelength, I know that the wavelength of my laser pen, because it tells me on it, my wavelength is 650 nanometers. So what that actually works out is 650 times 10 to the minus 9. So 650 times 10 to the minus 9. And what we're going to do, we're going to take a hypothetical distance that I'm going to be, from the slit to the screen is going to be 1.5 meters. So we're going to times that by 1.5 meters. So what we're going to do is we need to then work out the slit separation. So as I said, the slit separation needs to be really quite small. So we're going to take it, I'm going to make the slit separation, I'm going to make it 0.5 millimeter. So making it 0.5 millimeter is 0.5 times 10 to the minus 3. Hoping that everyone knows their standard form by now, they've got that into math. So obviously, 0.5 times 10 to the minus 3, all you need to do is just take your 0 and you hop it across. So it's minus 3, so we're going to the left, so it's 1, 2, 3, so you would end up with 0.0005, and that gives you 0.5 of a millimetre. If you're not quite sure what's going on with standard form, then ask your maths teacher. Alternatively, you can just work it. If it's a minus number, all you're doing is taking your decimal point from where it is, we're going left, and if there's no minus sign, you're going popping it right, however many numbers that you've got there. Okay, so this is what we're going to work out. This is what we need. So therefore, I need to go and get my calculator. So I need to get my calculator. So what we've got here is we've got our 600. Oh, it helps if I put my pen down, otherwise it's not going to let me do it. So we've got 650 times 10 to the minus 9. So if you don't figure this out how to do on your calculator, what you need to do is press the exponential button, which will be the button that's got EXP written on it. So 650, press the EXP, and it's minus 9. So you'll have a plus minus button, press that, and number 9, and then we're timesing that by our distance. Remember, distance is always in meters, so it's in 1.5 meters, so therefore we're timesing that by 1.5. And I've done that wrong because I pressed 5 twice, so hold on, give me 2 seconds. 650 exponential to the minus 9 multiplied by 1.5. So that gives you an answer of 0.000000975. What we need to do is divide that by our 0.5 times 10 to the minus 3, which again is in meters. The reason why it's in 10.5 to the minus 3 is because it's millimeters, but it has to be in meters. Distance is always in meters. So we're dividing that by 0.5 exponential button minus 3, which gives us an answer of 0.00195. Okay, so 0. Gives us an answer of 0.00195. And again, this is fringe spacing, so it's a spacing, so it is actually in the units of meters. So what we need to do is work out, so we've got our zeros, so that's 1, 2, 3. So what it actually is, it works out as 1.95 millimeters. So that would mean if I had my laser pen here, and I shone it through a barrier that had 2 slits in it that were 0.5 millimeter apart, and I put a screen 1.5 meters the other side of this, then the fringe spacing in between the slits and the interference pattern of my laser would be 1.95 millimeters. Okay, so that's how you work out fringe spacing. Obviously, you can rearrange this equation to work out if you know if you've taken you've tried it and you want to work out the wavelength of your pen. Then obviously you can rearrange this so you know the fringe spacing. You can find the fringe spacing. You then know your distance away from it, and you also know the slit separation because you've set up the slits as well. So you can obviously rearrange that to work out all of those from there. So that was our look at interference, the 2 types of interference, also the effects of what happens with single and double slit diffraction, which we're going to look a lot more in the next lesson, and also working out fringe spacing. That's the end of today's lesson. As I said, the next lesson, which is the last one, is looking at diffraction. A little bit more maths in that, nothing too intense though, and it'll be a little bit more full-on look at the single and double slit effects as well. So thanks for you for today's lesson. My name is Ian McDowell, I'm a student at University.